For our cubic model, the knowledge of this pattern is really going to help us out a lot. It's going to make things a lot easier, frankly, a lot easier than the quadratic model we kind of did from scratch. We know that we're going to have this pattern, right? So we have some coefficient times x minus a cubed, some coefficient times x minus a squared, some coefficient times x minus a plus d. All right? So for our cubic model, we're going to have these, we're going to set these conditions for what we consider to be a good cubic model. All right, so we're going to say that the function's values are equal, the first derivatives are equal, the second derivatives are equal, the third derivatives are equal at x equals a. Right, so when I say that the derivatives, I mean our model and the original function. So we're going to need the first, second, and third derivatives of this cubic. So I've done that here. All right, so when I find the first derivative, I go 3 times a, x minus a to the second power, and then 2 times b, x minus a to the first power. This just becomes c, and the d completely goes away as a 0. So that's the first derivative. And then when I take the derivative of that, so here's my first derivative. I take the derivative of that, I get my second derivative. I get 6a times x minus a plus 2b. And then when I take this derivative of that, I just get 6a. All right, so that's the first, second, and third derivatives of my cubic model. All right, and the nice part about this now, when we set the first derivative equal to the first derivative at x equals a, these x minus a terms make things a lot easier, because when x equals a, this quantity in any of those parentheses with the x minus a is always going to equal 0. Right, so when we say c of a has to equal f of a, well, if I look at the original, sorry, you can't see that. If I look at the original cubic, c of a is going to be a minus a is 0, a minus a is 0, a minus a is 0, only the d is left. So for c of a to equal f of a, our capital D has to equal f of a. Right, for the first derivative, here's our first derivative. So x minus a is 0. This term completely goes away. X minus a is 0. That term completely goes away. All that's left is c. So c has to equal the first derivative of f at x equals a, and so on. For the second derivative at a, x minus a is 0. That entire term goes away. All that's left is 2b. For the third derivative, I just have 6a equals the third derivative of f. So I can solve these easily for b. b is the second derivative of f at a over 2. a is the third derivative of f at a over 6. All right, so I've reordered my terms in this cubic, but it's the same cubic. It's a times x minus a cubed, b times x minus a squared, c times x minus a, and d. And I've spread them out here just so we can see them lined up over the corresponding terms of that cubic model when I substitute in the derivatives of f and the x minus a terms. All right, so that's a cubic model. We could do the fourth, fifth, sixth model, and it wouldn't really be as hard. That quadratic model was the toughest one because we kind of started from scratch, but now that we know this x minus a, the powers of x minus a pattern, makes it a lot easier. We're not going to keep doing that. Not too much farther. Here's our cubic model. Now I'm just going to look at the pattern, and I'm going to compare. I have my cubic model, and I want a fourth degree model. All right. What we're going to start to see here is that these are actually factorials. This is 2 factorial and 3 factorial. So we have second derivative over 2 factorial, third derivative over 3 factorial, fourth derivative. I'm going to use this parentheses 4 as the fourth derivative of f over 4 factorial. We're evaluating, sorry, this should be the fourth derivative of f at a. So the a should be up there. Over 4 factorial times x minus a to the fourth. All right, and this pattern, now that we have the fourth degree, we can really see this pattern start to take shape. This pattern itself is a Taylor polynomial. All right, this is how we get a polynomial approximation for any function to some degree is this way. We call this the nth Taylor polynomial, and it is the sum of these terms. K starts at 1 and goes to n. We have the k derivative evaluated at x equals a over k factorial times x minus a raised to the k power. That's our Taylor polynomial. So this is the general form for a Taylor polynomial of any function.